All right, let's talk about motional EMF. And just to be clear, these terms, we use them interchangeably when we're talking about electric potential. EMF, it stands for electromotive force, which is sort of an antiquated term. Nobody uses that anymore, but we're stuck still using EMF. Some textbooks never even tell you what it stands for. It's we don't use electromotive force anymore. But EMF, electric potential, voltage, those are all terms that we use interchangeably when we're talking about electric potential. So, induced potential, or EMF, in a conductor as it moves through a magnetic field. What happens? A conductor is full of charged particles, right? And they are free to move around. That's the definition of a conductor. So as this conductor moves to the right with some velocity v in a magnetic field into the page, what happens to those charged particles inside the conductor? Let's say the electron. There's an electron moving to the right, magnetic field's into the page. It feels a force, doesn't it? Charged particle moving in a magnetic field feels a force, and on an electron the force would be toward the bottom of the page, down. That's the magnetic force, F sub B. A positive charge would feel a force up. Okay, so what happens? Electrons start to move to the bottom. I'll draw some electrons down here. And what happens when they move to the bottom? They leave some positives behind. Eventually, what happens? Eventually, they reach some equilibrium, right? They stop moving. Why do they stop moving? Because this downward force from the magnetic field acts on that electron, but there are a bunch of electrons already here repelling it. So there's an electric force in the upward direction due to the charges that have already moved. Right? There's an attractive force from the positives up there and a repulsive force from the negatives down here. So the first electron, it's a no-brainer. It moves because there's a magnetic force. Then the second electron sees a little bit of repulsion, but the magnetic force is bigger, so it moves. The third electron, right? They keep moving as long as the magnetic force is bigger than the electric force. And at some point, they stop moving because those two forces balance. So let's see when that occurs. We say the electric force is equal to the magnetic force. And what is the electric force? It's the charge times the electric field. And the magnetic force is Q, V, B, and the sine of 90 degrees is just 1. I'll leave that out. And this little v is the velocity. And we can make this substitution. The electric field is the change in voltage over the distance, right? We use that. E equals minus delta V, where this is the voltage, capital V, over some distance, S or L or X. So I'm going to substitute in here, and I'm going to use a script E for the voltage because I've already got a V for my velocity. If I have a V for my voltage, it's going to get a little confusing. So I'm going to use this script E for EMF that we use a lot. So that's the voltage divided by the length, the distance between the positives and the negatives. And that gives me the electric field inside the rod. And that has to equal QVB. The charge cancels. And I get the potential generated across that rod is just V times B times the length of the rod. And we call that motional EMF because it's due to the motion of the conductor in the electric field. The charges move due to the motion of the conductor in the magnetic field. And it creates this potential across the rod.